The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, yesterday we saw how to define double integrals and how to start computing them in terms of x and y coordinates. Okay? So we've defined the double integral over a region in plane of a function f of xy dA. You can't hear me? Okay. Is the sound working? Can you hear me at the back now? Can we make the sound louder? Does this work? And people are not hearing me at the back. Is it better? Okay, people are still saying make it louder. Is it better? Okay, great. Thanks. So, okay, that's not an excuse to start, chatting with your friends. Thanks. Okay, so when we have a region in the xy plane, and we have a function of x and y, we are defining the double integral of f over this region by taking basically the sum of the values of a function everywhere in here times the area element. And the definition actually is we split the region into lots of tiny little pieces. We multiply the value of the function at that point times the area of a little piece, and we sum that everywhere. And we've seen actually how to compute these things as iterated integrals. So first integrating over dy, then over dx, or the other way around. So one example that we did in particular was to compute the double integral over a quarter disk, quarter of a unit disk. So that was the region where x squared plus y squared is less than 1, and x and y are positive, of 1 minus x squared minus y squared dA. And, well, hopefully I kind of convinced you that we can do it using enough trig and substitutions and so on, but it's not very pleasant. And the reason for that is that using x and y coordinates here doesn't seem very appropriate. So in fact, we can use polar coordinates instead to compute this double integral. So remember that polar coordinates are about replacing x and y as coordinates for a point in the plane by instead r, which is the distance from the origin to our point, and theta, which is the angle measured counterclockwise from the positive x-axis. Okay, so in terms of r and theta, you have x equals r cosine theta, y equals r sine theta. So the claim is we are able actually to do double integrals in polar coordinates. We just have to learn how to. Okay, so just to draw a quick picture, when we were integrating in xy coordinates, in rectangular coordinates, we were slicing our region by grid lines that were either horizontal or vertical, and we used that to set up the iterated integral. And we said dA became dx dy or dy dx. So now we are going to actually integrate in terms of the polar coordinates, r and theta. So let's say we will integrate in the order, well, r first and then theta. That's the order that makes the most sense usually when you do polar coordinates. So what does that mean? It means that we will first focus on a slice where we fix the value of theta. and we'll let r vary. So that means we fix a direction, we fix a ray out from the origin in a certain direction. And we'll travel along this ray and see which part of it, which values of r are in our region. Okay, so here it will be actually pretty easy, because r will just, well, start at 0, and you'll have to stop when you actually exit this quarter disk. Well, what's the equation of this circle in polar coordinates? It's just r equals 1. So we'll stop when r reaches 1. Okay. What about theta? Well, the first ray that we might want to consider is the one that goes along the x-axis. That's when theta equals 0. And we'll stop when theta reaches pi over 2, because we don't care about the rest of the disk. We only care about the first quadrant. Okay, so we'll stop at pi over 2. Now, there's a catch, though, which is that dA is not dr d theta. So let me explain to you why. Okay? So let's say that we are slicing, what it means really is that we are cutting our region into little pieces that are the elementary, what corresponds to a small rectangle in the xy coordinate system. Here would be actually a little piece of circle between a given radius r and r plus delta r, and given between an angle theta and theta plus delta theta. Okay, so I need to draw actually a bigger picture of that, because it's really hard to read. So let's say that I fix an angle theta and a slightly different one where I've added delta theta to it. And let's say that I have a radius r and I add delta r to it. So then, I'll have a little piece of xy plane that's in here, and I have to figure out what is its area. What is delta A for this guy? Well, let's see. This guy actually, if, my delta r and delta theta are small enough, it will almost look like a rectangle. It's rotated, but it's basically a rectangle. I mean, these sides, of course, are curvy, but if they're short enough, it's almost straight. So the area here should be this length times that length. Well, what's this length? That one is easy. It's delta r. Okay? So what about that length? Well, it's not delta theta. It's something slightly different. It's a piece of a circle of radius r corresponding to angle delta theta. So it's r delta theta. So times r delta theta. Okay, so that means now even if we shrink things and take smaller and smaller regions, dA is going to be r dr d theta. Okay, so that's the important thing to remember. When you integrate in polar coordinates, you just set up your bounds in terms of r and theta, but you replace dA by r dr d theta, not just dr d theta. And then, of course, we have some function that we're integrating. Let's say that I called that thing f. Then it's the same f that I put up here. Oops. So concretely, how do I do it here? Well, my function f was given as, 1 minus x squared minus y squared. And I'd like to switch that to polar coordinates. I want to put r and theta in there. Well, I have formulas for x and y in polar coordinates. So I could just replace, x squared by r squared cosine square theta, y squared by r squared sine square theta. And that works just fine. But maybe you can observe that this is actually, this is x squared plus y squared. It's just the square of the distance from the origin. So that's just r squared. Okay, that's a useful thing. You don't strictly need it, but it's much faster if you see this right away. Saves you, writing down a sine and a cosine. So now we just end up with the integral from 0 to pi over 2, integral from 0 to 1 of 1 minus r squared r dr d theta. Now, if I want to compute this integral, so let's first do the inner integral. So if I integrate r minus r cubed, I will get r squared over 2 minus r squared over, r to the 4 over 4 between 0 and 1. And then I will integrate d theta. So what is this equal to? Well, for r equals 1, you get 1/2 minus a quarter. That's going to be just a quarter. And when you plug 0, you get 0. So it's the integral from 0 to pi over 2 of 1/4 d theta. And that just integrates to a quarter of pi over 2, which is pi over 8. OK? So that's a lot easier than the way we did it yesterday. Now, well, here we were lucky, OK? I mean, usually you will switch to polar coordinates either because the region is easier to set up. Here it's indeed easier to set up because, see, the bounds became very simple. We don't have that square root of 1 minus x squared anymore. Or because the integrand becomes much simpler. Here, our function, well, it's not very complicated in x, y coordinates, but it's even simpler in r theta coordinates. So here we were very lucky. In general, there's maybe a trade-off. Maybe it will be easier to set up the bounds, but maybe the function will become harder because it will have all these sines and cosines in it. If our function had been just x is very easy in x, y coordinates. Here it becomes r cosine theta. That means you will have a little bit of trick to do in the integral. Not a very big one, but not a very complicated integral. But imagine, it could get potentially much harder. Okay, so anyway, that's double integrals in polar coordinates. And the way that you set up the bounds in general is, so in 99% of the cases, you will integrate over r first. So what you will do is you will look for a given theta. What are the bounds for r to be in the region? What is the portion of my ray that's in the given region? And then you will put the bounds for theta. But conceptually, it's the same as before. Just instead of slicing horizontally or vertically, we slice radially. Okay? So we'll do more examples in a bit. Any questions about this or the general method? Yes?
When you say you're computing the rectangle when they get smaller and smaller into the rectangle, I'm curious why you use R theta instead of R plus delta R?
Yes. So that's a very good question. OK. Yes, why do I measure the length inside instead of outside? Oops, which one do I want? This one. So here I said this side is r delta theta. I could have said, actually, r delta theta is the length here. Here it's a slightly more. It's r plus delta r times delta theta. But if delta r is very small compared to r, then that's almost the same thing. And this is an approximation anyway. So I took this one because it gives me the simpler formula. If you take the limit as delta r tends to 0, then the two things become the same anyway. Okay? The length, whether you put r or r plus delta r in here doesn't matter anymore. If you imagine that this guy is infinitely small, then really the lengths become the same. Okay, we'll also see another proof of this formula using changes of variables next week. But I mean, hopefully this is at least slightly convincing. Okay, more questions? No? Okay, so let's see. So we've seen how to compute double integrals. I have to tell you what they're good for as well. So the definition we saw yesterday and motivation was in terms of finding volumes. Okay? But that's not going to be our main preoccupation because finding volumes is fun, but it's not all there is to life. And now, you're doing single integrals. When you do single integrals, it's usually not to find the area of some region of a plane. It's for something else, usually. Okay? So the way we actually think of a double integral is really as summing the values of a function all over this region. So we can use that to get information about maybe the region or about the average value of a function in that region and so on. So let's think about various uses of double integrals. So the first one that I will mention is actually something you thought maybe you could do with a simple integral, with a single integral. But it's useful very often to do it as a double integral. It's to find the area of a given region R. Okay, so I give you, some region in the plane, and you want to know just its area. So in various cases, you could set this up as a single integral. But often it could be useful to set it up as a double integral. So how do you express the area as a double integral? Well, the area of this region is the sum of the areas of all the little pieces. So it means you want to sum one dA over the entire region. Okay, so the area of R is the double integral over R of the function 1. So one way to think about it, if you're really still attached to the idea of double integral as a volume, what this measures is the volume below the graph of a function 1. The graph of a function 1 is just a horizontal plane at height 1. So what you'll be measuring would be the volume of a prism or with base R and height 1. And the volume of that, of course, would be base times height, so it would just be the area of R again. But we don't actually even need to think about it that way. Really, what we're doing is we're summing dA over the entire region. Okay, a related thing we can do, so imagine that actually this is, some object, some physical object. I mean, it's got to be a flat object because we're just dealing with things in the plane so far. But you have a flat metal plate or something, and you would like to know its mass. Well, its mass is the sum of the masses of everything, every single little piece. And so you would get that by integrating the density. The density for a flat object would be the mass per unit area. Okay, so you can get the mass of a flat object with density. So let's use delta for density, which is the mass per unit area. So each little piece of your object will have a mass, which will be just the density times its area for each small piece. And you will get the total mass by summing these things. So the mass will be the double integral of the density times the area element. Now, if it has constant density, if it's always the same material, then of course you could just take the density out and you will get density times the total area. If you know that it's always the same material. But if actually it has varying density, maybe because it's some metallic thing but with various metals or with varying thickness or something, then you can still get the mass by integrating the density. Okay? So, of course, looking at flat objects might be a little bit strange. That's because we're only doing double integrals so far. In a few weeks, we'll be doing triple integrals, and then we'll be able to do solids in space. But, one thing at a time. Okay? So, okay. Another useful application is to find the average value of some quantity in a region. So what does it mean to take the average value of some function f in this region R? Well, you know what's the average of a finite set of data. For example, if I ask you to compute your average score on 1802 problem sets, you would just take the scores, add them up, and divide by the number of problem sets. What if there's infinitely many things? Because, say I ask you to find the average temperature in this room, well, you would have to measure the temperature everywhere, and then add all of these together and divide by the number of data points. But depending on how careful you are, actually, there's potentially infinitely many points to look at. So the mathematical way to define the average over a continuous set of data is that you actually integrate the function over the entire set of data, and then you divide by the size of the sample, which is just the area of the region. Okay, so in fact, the average of f, so the notation we'll use usually for that is f with a bar on top, okay, to tell us it's the average f. That would be, so we said we'll take the integral of f and we'll divide by the area of the region. Okay, you can really think of it as the sum of the values of f everywhere divided by the number of points in everywhere. And so that's an average where everything is actually equally likely. That's a uniform average where all the points in the region, all the little pieces of the region are equally likely. But maybe if you want to do, say, an average over some solid with variable density, or if you want to somehow give more importance to certain parts than to others, then you could actually do a weighted average. So what's a weighted average? Well, in the case of taking the average of your problem sets, if I tell you, well, problem set 1 is worth twice as much as the others, then you would count twice that score in the sum, and then you would divide. You would count it as 2, of course, when you divide. So the weighted average is the sum of the values, but each weighted by a certain coefficient, and then you will divide by the sum of the weights. So it's a bit the same idea as when we replace area by some mass that tells you how important a given piece is. So we'll actually have a density. Let's call it delta again. That would be now, well, we'll see what we divide by. But what we will take is the integral times of a function times the density times the area element. Because this would correspond to the mass element, telling us how to weight the various points of our region. And then we would divide by the total weight, which is the mass of the region. So as defined up there. Okay? So, if the density is uniform, then of course the density gets out and, you can simplify and reduce to that if all the points are equally likely. Okay, so why is that important? Well, that's important for various applications, but one that you might have seen in physics, we care about maybe where is the center of mass of a given object. Okay, so the center of mass is basically the point, you would call that point to be, you would say that point is right in the middle of the object. But of course, if the object has a very strange shape, or if somehow part of it is heavier than the rest, then that takes a very different meaning. So strictly speaking, the center of mass of a solid is the point where you would have to concentrate all the mass if you wanted it to behave equivalently from the point of view of mechanics, if you are trying to do translations of that object. If you are going to push that object, that would be really where, where the equivalent point mass would lie. The other way to think about it, if I have a flat object, then the center of mass is basically the point where I would need to hold it so that it's perfectly balanced. And of course, I can't do this because I'm not, well, whatever. But you get the feeling. I mean, the center of mass of this eraser is somewhere in the middle. And so in principle, that's where I would have to put my finger for it to stay. Well, and it doesn't work. Okay, but that's where the center of mass should be. I think it should be in the middle. So well, maybe I shouldn't call this 3. I should call this maybe, 2a or whatever. Because it's really a special case of the average value. So how do we find the center of mass of a flat object with density delta? Well, so if you have your object in the xy plane, then its center of mass will be at positions that are actually just the coordinates of the center of mass will just be the weighted averages of x and y on the solid. Okay, so the center of mass will be at a position that I will call x bar, y bar, and these are really just the averages, the average values of x and of y in the solid. So just to give the formulas again, x bar would be 1 over the mass times the double integral of x times density dA. Okay, and same thing with y. Y bar is the weighted average of the y coordinate in your region. Okay, so you see, if you take a region that's symmetric and has uniform density, that will just give you the center of the region. But if the region has a strange shape, or if the density is not homogeneous, if parts of it are heavier, then you will get whatever the weighted average will be. And that would be the point where this thing would be balanced if you were trying to balance it on a pole or on your finger. Okay? Any questions so far? No? Yes?
When you do that double integral over here, the inner one is y, the outer one is
No, sorry. No. So when you do, so here I set up this, I didn't set this up as an iterated integral yet. Okay? So here, the function that I'm integrating is x times delta, where delta, the density, will be given to me maybe as a function of x and y. And then I will integrate this dA. And dA could mean dx dy, could mean dy dx, could mean r dr d theta. I will choose how to set it up depending maybe on the shape of the region. If my solid is actually just, going to be round, then I might want to use polar coordinates. If it's a square, I might want to use xy coordinates. If it's more complicated, well, I will choose depending on how I feel about it. Yes? Yes, so delta is the density. It's in general, it's a function of x and y. If you imagine that your solid, is not homogeneous, then its density will depend on which piece of it you're looking at. Of course, to compute this, you need to know the density. If you have a problem asking you to find the center of mass of something and you have no information about the density, assume it's uniform. Take the density to be a constant. Even take it to be a 1. That's even easier if you want. It's a general fact of math. We don't care about units. So density, if density is constant, we might as well take it to be 1. And that just means that our mass unit becomes the area unit. Yes?
So you have written in general the center of mass, but using x and y coordinates. If we wanted to use polar coordinates, would we just substitute our data for x and
That's a good question. No, I don't think we could actually find the center of mass in polar coordinates by finding the average of r or the average of theta. See, for example, take a disk centered at the origin. Okay, well, you know that the center of mass should be at the origin, right? But the average of r is certainly not 0 because r is positive everywhere. So that doesn't work. You cannot get the polar coordinates of the center of mass just by taking the average of r and the average of theta. By the way, what's the average of theta? You know, if you take theta to go from 0 to 2 pi, the average theta will be pi. If you take it to go from minus pi to pi, the average theta will be 0. So there's a problem there. So that actually just doesn't work. So we really have to compute x bar and y bar. But still, we could compute them. You know, we could set this up and then switch to polar coordinates to evaluate this integral. But we'd still be computing the average values of x and y. Okay. So the next thing, so we're basically re-exploring, you know, mechanics and motion of solids here. So the next thing is moment of inertia. So just to remind you, or in case you somehow haven't seen it in physics yet, so the moment of inertia is basically to rotation of a solid what the mass is to translation. Okay? In the following sense, the mass of a solid is what makes it hard to push it. You know, how hard it is to throw something is related to its mass. How hard it is to spin something, on the other hand, is given by its moment of inertia. Maybe I should write this down. So mass is how hard it is to impart a translation motion to a solid. So I'm using fancy words today. And the moment of inertia, so the difference with the mass is that the moment of inertia is defined about some axis. Okay, so you choose an axis, and then you will try to measure how hard it is to spin your object around that axis. For example, I can try to measure how hard it is to spin this sheet of paper about an axis that's in the center of it. So I will try to spin it like that and see how much effort I have to make. Well, for a sheet of paper, not very much. But so that would measure the same thing, but it would be rotation motion about that axis. So maybe some of you know the definition. If not, I'm going to try to derive it again. I'm sorry that it won't be quite as detailed as the way you've probably seen it in physics, but you know, I'm not trying to replace your physics teachers. I'm sure they're doing a great job. And so, you know, what's the idea for the definition? To find a formula for moment of inertia. So the idea is to think about kinetic energy. Kinetic energy is really what, when you push something or when you try to make it move, you have to provide some energy to it, and then it has kinetic energy. And if you have the right device, then you can convert back that kinetic energy into something else. So if you try to look at the kinetic energy of a point mass, so you have something with mass m going at velocity v, well, that will be 1/2 of the mass times the square of the speed. Okay, hopefully you've all seen that formula sometime before. Now let's say that instead of just trying to push this mass, I'm going to make it spin around something. Okay, so instead of just going somewhere, maybe I will have here the origin, and I'm trying to actually make it go around the origin at a certain, in a circle, at a certain angular velocity. So for a mass m at distance r, let's call r this distance. And angular velocity, let's call the angular velocity omega. I think that's what physicists call it. So remember, the angular velocity is just the rate of change of the angle over time. Okay? It's d theta dt, if you want. Well, what's the kinetic energy now? Well, first we have to find out what's the speed. What's the speed? Well, if we are going on a circle of radius r at angular velocity omega, that means that in unit time we rotate by omega and we go by a distance of r times omega. Okay? So the actual speed is the radius times the angular velocity. And so the kinetic energy is 1/2 mv squared, which is 1/2 m r squared omega squared. And so, see, by similarity with that formula, we can think of, so here the coefficient of v squared is the mass. And here we'll say the coefficient of omega squared, so this thing, is the moment of inertia. That's how we define the moment of inertia. Okay, now that's only for a point mass. And it's kind of fun to spin just a small ball, but maybe you'd like to spin actually a larger solid and try to define this moment of inertia. Well, the moment of inertia of a solid will be just the sum of the moments of inertia of all the little pieces. So what we'll do is we'll just cut our solid into little chunks and we'll sum this thing for each little piece. Okay, so for a solid with density delta, so each little piece has mass, which is the density times the amount of area. I guess it's equal, actually. And the moment of inertia of that small portion of the solid will be delta m, the small mass, times r squared, the square of the distance to the center, to the axis around which I'm spinning. So that means if I sum these things together, well, so has moment of inertia delta m times r squared, which is r squared times the density times delta a. And so I will be summing these things together. And so the moment of inertia about the origin will be the double integral of r squared times density times dA. Okay, so the final formula for the moment of inertia about the origin is the double integral over the region of r squared density dA. Or if you prefer, if you're going to do it in xy coordinates, of course, r squared becomes x squared plus y squared. It's the square of the distance from the origin. Okay, so when you integrate this, that tells you how hard it is to spin that solid about the origin. So the motion that we try to do is we keep this fixed, and then we just rotate around the origin. Well, sorry, that's a pretty bad picture, but hopefully you get what I mean. Okay. And then the rotational energy, so the name we use for that is I0. And then the rotational kinetic energy is 1/2 times this moment of inertia times the square of the angular velocity. So it's in this sense that this replaces the mass. for rotation motions. Okay. What about other kinds of rotations? So in particular, here we've been rotating things about just a point in the plane. What you could imagine also is instead you have your solid. So what I've done so far is I've skewered it this way, and I'm rotating around the axis. Instead, I could skewer it through, say, the horizontal axis, and then I could try to spin about the horizontal axis. So then it would, rotate in space in that direction, like that. So let's say we do rotation about the x-axis. Well, the idea would still be the same. Okay? The moment of inertia for any small piece of the solid would be its mass element times the square of the distance to the axis, because that will be the radius of the trajectory. If you take this point here, it's going to go on a circle like that, centered on the x-axis. So the radius will just be this distance here. Well, what's this distance? It's just y, or maybe absolute value of y. Okay, so distance to x-axis is absolute value of y, and what we actually care about is the square of the distance. So that will just be y squared. So the moment of inertia about the x-axis is going to be obtained by integrating y squared times the mass element. Okay? It's slightly strange that I have y in the inertia about the x-axis, but if you think about it, y tells me how far I am from the x-axis, so how hard it will be to spin around the x-axis. Okay? And I could do the same about any other axis that I want, just I would have to sum the square of the distance to the axis of rotation. Okay, so maybe I should do an example. Yes?
What do you square on the left?
Oh, sorry, same thing as above, distance to the x-axis. Because that's what we care about, right? For the moment of inertia, we want the square of the distance to the axis of rotation. Okay, so let's do an example. Let's try to figure out if we have just a uniform disk, how hard it is to spin it around its center. Okay, so that shouldn't be very hard to figure out. Say that we have a disk of radius a, and we want to rotate it about its center. And let's say that it's of uniform density, and let's take just the density to be 1, so that we don't really care about the density. So what's the moment of inertia of that? Well, we have to integrate over our disk r squared times the density, which is 1, times dA. Okay, what's r squared? So you have here to resist the urge to say, oh, the radius is just a. We know the radius is a. No, it's not a, because we're looking at rotation of any point inside this disk. And when you're inside the disk, the distance to the origin is not a, it's less than a. It's actually anything between 0 and a. Okay, so just to point out a pitfall, r here is really a function on this disk, and we're going to integrate that function. Okay, don't plug r equals a just yet. Okay, what coordinates do we use to compute this integral? Yeah, probably polar coordinates. I mean, unless you want a repeat of what happened already with, x and y. So that will tell us we want to integrate r squared times r dr d theta. And the bounds for r, well, r will go from 0 to a, no matter in which direction I go from the origin, if I fix theta, r goes from 0 to r equals a. The part of this ray that lives inside the disk is always from 0 to a. And theta goes from, well, 0 to 2 pi, for example. Okay? And now you can compute this integral. Well, I'll let you figure it out, but the inner integral becomes a to the 4 over 4, and the outer multiplies things by 2 pi, so you get pi a to the 4 over 2. No, yes. Okay, so that's how hard it is to spin this disk. Now, what about, instead of spinning it about the center, we decide actually to spin it about a point on the circumference. So, for example, think of a frisbee. It has this rim, and so you can actually try to make it rotate around a point on the circumference by holding it, near the rim and spinning it there. How much harder is that than around the center? Well, we'll try to compute now the moment of inertia about this point. So we have two options. One is we keep the system of coordinates centered here, but then the formula for distance to this point becomes harder. The other option, which is the one I will choose, is to change the coordinates so that this point becomes the origin. Okay, so let's do that. So about a point on the circumference, what I would have to do maybe is set up my region like that. Now I've moved the origin so that it's on the circumference of the disk. And I will again try to find the moment of inertia of this disk about the origin. So it's still the double integral of r squared dA. But now I want to find out how to set up the integral. So I could try to use xy coordinates, and it would work. Or I can use polar coordinates, and actually it works a little bit better that way. But both are doable. So let's say I do it this way. So I have to figure out how to set up my bounds, right? So what are the bounds for r? Well, if I fix a value of theta, so it means I chose an angle here, and now I'm shooting a ray from the origin in that direction. So I enter my region at r equals 0, but hasn't changed. Question is, where do I exit the region? So what is that distance? Okay, so maybe you've seen it in recitation, maybe not. So let's see. Well, actually, I should have written down the radius of the circle is a, so this distance here is 2a. Okay, so if you draw this segment in here, you know that here you have a right angle. So you have a right triangle. The hypotenuse here has length 2a. This angle is theta. Well, this length is 2a cosine theta. Okay. So the polar coordinates equation of this circle passing through the origin is r equals 2a cosine theta. So r will go from 0 to 2a cosine theta. Okay? That's the distance here. Now, what are the bounds for theta? It's not quite 0 to 2 pi because actually, you see, in this direction, if I shoot a ray in this direction, I will never meet my region. So I have to actually think a bit more. Well, the directions in which I will actually hit my circle are all the directions in the right half of the plane. Okay, I mean, of course, if I shoot very close to the axis, you might think, oh, I won't be in there, but actually that's not true because here the circle is tangent to the axis. So really, no matter which direction I take, I will still have a little tiny piece. So the angle actually goes from minus pi over 2 to pi over 2. So now if you compute that, you will get, well, the inner integral will be r to the 4 over 4 between 0 and 2a cosine theta, which will turn out to be 4a to the 4 cosine to the 4 theta. And now you will integrate that from minus pi over 2 to pi over 2. And, well, that's again the evil integral that we had yesterday. So either we remember the method from yesterday, or we remember from yesterday that actually there's formulas in the notes to help you. So on homework, you can use these formulas in the notes. At the beginning of section 3b, there's formulas for these particular kinds of integrals. And that will end up being 3/2 of pi a to the 4. So in case you wanted to know, it's 3 times harder to spin a Frisbee about a point on its circumference than around the center. See, we got 3 times the moment of inertia about the center. Okay, that's it. Have a nice weekend.